Okay, thank you very much. Thank you for the invitation. This is not a typical audience for me, so I try to convey to you what we do at the fundamental research level. And I'm not really close yet to use this for networking, but we can discuss how this could be extended afterwards at the end. Okay, so I give you a first overview of so what we want to do basically is we want to manipulate photons, and to manipulate the photons we use atoms. Okay, and there are different ways how to play with this, and the initial idea for me was to trap the photons like in a sponge. So you take a sponge, you go in the sun, you take the photons and then go in the basement, and then you squeeze the punch and the photons will come out. So how can we do this? And I use the sponge picture like a random system because we don't have a cavity. So it's a little bit a different way from what people usually do. So that's basically the idea of this talk, and I will walk you through the different ways how to understand this and how to do it with hardware, physically. And so first, I want to acknowledge the people. So I'm usually considered by those people as the salesman. So I'm the businessman of this company. Basically, it's a small company with 6 permanent people. We'll come back to them, and they always consider that I'm the crazy guy. I'm selling crazy ideas, and I can only do this because they do the hard work in the lab. If they would not work in the lab, I could not sell products. And our products are ideas and results and papers. So that's basically what we do. So William Guérin, and so those who visited yesterday saw Raphaël Saint-Jalm, who presented one of the cold atom experiment, ytterbium. Guillaume Labéry was actually the first one to join the team when we came to Nice more than 20 years ago, and he did the first multiple scattering experiment in cold atoms in our team. Anders Kasberg joined the team later on. He was working on quantum memories with cold atoms, but now he's passed to something else. And Willem Guérin and Mathilde Hugbard, they're in charge of one rubidium cold atom experiment. William Guérin, I will present some of his experiments, is going to see how to do gates with this. And Mathilde is looking at quantum optics beyond, so like entanglement coming out of photons which have been produced by cold atom samples. So these people are really doing they're in charge of their own projects, and I'm somehow coordinating all this stuff. And we have right now a couple of postdocs and a couple of PhD students who, of course, are essential. And as you might always know, that the success of all these type of results depends on the PIs, but also very strongly on the excellence of the PhD students and the postdocs. And this is not an easy task, in particular here in Nice. So if you have good students to send us to Nice, we are happy. Our main limitation is the quality of the students, basically. That's what is really the hardware. It's not the money, really, right now. It's the quality of the students. And as I like to travel a lot. I like to collaborate a lot with other people. And this is a list of collaborations we have right now. And these are more or less all active collaborations, which keep me busy in interacting with other people. But I always think, and I always take the time for the first slide here on my speaking time, but I think it's important. It's important to speak to people outside of your group, of your lab, and outside of your country, because there are different ways how to approach science. And this gives you new ideas how to do things. Even if you have your roadmap, I have a roadmap, Anders localization. But how to go there and what to see on the site, it's important to get independent input. And so I got input from many other people, and some people joined our effort, which came from very different physics, nuclear physics, high energy physics, and they get new ideas to this whole physics. So it's very interesting. Of course, also when you sign papers, if you do something which is on the edge or where you're sure or not sure, having other people signing your papers, they are on board. So they sync with you if you sync, or they sail with you if you sail far away. And this also different countries and different people from different background, I think is really important. And I always push the students to spend at least 1 month in the group outside, because if a student has to go outside, he has to be able to present what they do at home to different people. So that's super important, because in our group, we basically all know what we're doing, and the students get a little bit lazy to understand the depths of what they do. If they have to explain this to one of those people here, they have to explain everything from zero. So it's a super good training for students to go somewhere else. So I'm really a very, very strong advocate of collaborations and sending people from one group to another group. Okay, so it takes time, but I think it's important. Okay, so what we do in our group, so we started the cold atom activity in Nice almost 30 years ago, and our working horse was to trap atoms. So this is a trap of cold atoms. So this is maybe 10 to the 10 atoms of rubidium at a few hundred microkelvin temperature. So it's a trap of cold atoms. And so the idea of what we did is, compared to all the rest of the community at that time and even now, we want to trap many atoms. There's a strong community in cold atoms which is doing Bose-Einstein condensate, so that has been rewarded by Nobel Prizes and so on, so very important. We try to focus on something else, and our specialty is to trap many atoms. And as Phil Anderson said, more is different. Typically, if you get a larger scale system, you go from single atom physics to collective effects, and you get new qualitative features coming out. And I will speak about this, but so, for instance, one thing we do here is pattern formation, it's self-organization, so atoms arrange themselves in regular patterns, so we can do magnetism studies on this. It's all based on these experiments. We can do plasma physics, where we get the multiple scattering of light is like Coulomb interactions at some point, so you can have the equivalent to plasma physics and turbulence. And somehow we also do now with hot vapors, we do quantum fluids of light, and we also, because we were interested in intensity correlations, we went to astrophysics, and now we bring this expertise and the hardware we use in the lab to telescopes in different places. Okay, but so I will speak today, I will focus on this year. It's how to keep a photon in the system for a long time. So how to trap a photon with many atoms. That's the goal of the talk today. And the take-home message is shown here. So if you want to just to remember one thing of this talk is this. So the question is how to keep a photon in a large assembly of scatterers for a long time. So I will assume that all of you are cold atoms, okay? So now the question is, I now have a photon here, so how can I keep the photon here for a long time? So one way is I throw a photon at someone, and then there will be random walk, just a classical random walk from one place to the other place, diffusion process. And this is what is happening here. It's just a classical diffusion process. You get an opaque medium, and the larger the system, the longer it will take for this photon to go to the border, and then it can escape. Okay, so that's one way to keep the photon in the system for a long time, just random multiple scattering event. But there's no interference effect involved in this. It's interesting by itself, but we want to go beyond this. And there are two other ways which have been proposed to keep the photon in the sample for a long time. One is our holy grail is underlocalization, and the idea is that if you have some atoms here, they will share photons. There will be interference effects like a small cavity here, so the photon will be shared by these atoms here, and the other atoms will not know that there's a photon here. So it's a localized excitation, localized spatially confined in the subpart of the region, and due to interference effect, photons will stay in part of the cloud. So that's underlocalization. And the other way is Dicke subradiance, and the idea is that there's a photon which is shared among all of you. So all of you know that there's a photon, but you oscillate out in phase in a convenient way that is an interference effect which prevents the photon to leave. So this is an extended state, but still keeps the photon in the system for a long time. So there's three different ways how to keep a photon in the system for a long time. And we want to understand if this is just a different way how to think about it, or if there are phase transitions between these systems and how to control it in practice in hardware. So that's the goal. Okay, so what we do is, so people study this type of physics with very different samples. Condensed matter, so white paint, or semiconductor powders, biological sample, whatever sample you have, you can try to study this. And what we do is we try to use cold atoms as a sample to study all this type of physics. Okay, and so as I said, the holy grail is Anders localization. So every now and then it's good to get back to the initial papers, which is sometimes people forget to read the papers, which were the founding papers. So our founding paper, it's a paper by Phil Anderson in '58, where he actually was looking at what happens if you have a conductor and what's the transition between a conductor and insulator for electrons. And he came up with a model, which is written here. So I hope that you're not afraid too much of equations. There will be not so many equations, but some equations. So this is the equation of the amplitude of an electron on the side. So we consider the lattice with different size j, and that's the amplitude of the electron wave function on lattice on side j. And the evolution of this is given by this equation here. So that's the energy on every lattice side, and this is the hopping from one lattice side to the other lattice side. Okay, and so what he showed is that depending on the connectivity, how much you can jump from one side to the other, and how much disorder you put on every energy on every side, at some point there's a transition where if you have sufficient amount of disorder on the energy on the lattice side, the wave function will not spread, but will be frozen and localized, as I mentioned, in a subpart of the region. So this is, okay, that was a very important paper because this showed that disorder can really make a transition between a conductor and an insulator. And so people have been studying this initially for electrons, but electrons also have a lot of Coulomb interactions. So this here is a non-interacting wave equation. And so people very quickly went away to study this effect from electrons and try to get non-interacting waves. And okay, so the people who are doing this with acoustics, with matter waves, we go for photons. Photons are a very nice sample to study these type of things. And so there have been, particularly for photons, there have been different papers which are often cited, like this paper is often cited for a wrong reason, but it's cited, and we also cite it. It's the wrong reason why we cite this. This is the so-called Joffe-Regel paper, which says that if KL is order of 1, so K is 2 pi over lambda, it's a wave number, okay? And L is the mean free path. How far does the wave propagate before it changes direction? And in this paper, basically what they say is that if KL is over 1, our standard models no longer apply. So you have to do something else. We don't know how to solve the problem if KL is of order of 1 or smaller. So if this means if the photon scatters at the distance of the wavelength, then things change. But he doesn't speak about localization at all. But everyone cites this paper to say if KL is order of 1, then you might get Anders localization, which is actually correct in some region, but it was not in this paper. Then there's another paper which is important, and I mentioned this because, at least for light scattering, this is something which at present is not well recognized in the community. So it says that there are two ways how to do disorder. One is random electric fields, which corresponds to what I presented on the previous slide on-site disorder on every energy side for the electron swapping from one side to the other. So it's an energy disorder on every side. And then there's fluctuations in density, which produce the disorder how far you travel. If you have a piece of glass with fluctuations in the density of glass, they will scatter on the fluctuation of density. And so that's a different type of disorder. It's not the on-site energy disorder, but it's a disorder on fluctuation in density. And this is mapping on this Joffe-Regel criterion, how far you propagate. It's different concepts. And typically people from different communities use either one or the other type of disorder to try to get localization. For light, so far, only this type of disorder, fluctuation density, has been used, and this has not been used. And at the end of my talk, I will come back to this, that we want to now to explore both approaches to localization. Okay, so all these are quite old papers, so typically most people don't know them in the community. Okay, so localization of light has been discussed very quickly, very fastly in the 80s. People have mentioned that photons don't interact, so it's a good way to study this localization problem of non-interacting waves. And there have been pioneers, dinosaurs of this community who have spent their career to look for this. One of these early pioneers was at Lagendijk in Netherlands. And so he used semiconductor powders because they have very high index of refraction, so it's very efficient scatterer. So it's easy to scatter in the mean free path, in the near field. So KL of order of 1 is easier to get with semiconductor powders because of this high index of refraction. And so he looked at how much light is going through the sample, because if you have an insulator, then the transmission will go down exponentially, and if you have a conductor, it will go down only as 1 over L, so it's Ohm's law for transmission. And he found a signature which would be consistent with Anders' localization, so we're very happy, published this in Nature. And very quickly there was a comment by Frank Schaffold and Georg Maret, basically this, and they said, well, what you see here can also be explained by absorption. Semiconductors have a lot of absorption, and so there was a technical issue with absorption, and they said, all what you see, we can explain it just by absorption, not by localization. And a couple of years later, at Lagendijk in this paper, they redid some experiments and they say, yes, you're right. Okay, so this was basically can be explained by absorption. It doesn't mean that its localization is not present, but the signature can be explained by absorption. Okay. Then Georg Maret of this comment here, he got a different idea to get rid of absorption. He went for time-dependent experiments. And then somehow you can normalize out the residual absorption. And he also uses white paint, which has much less absorption. He compresses the white paint, TiO2, very densely. And he looked at how long photons stay in the system. And the red line here would be the precision of the random walk model. And he saw some photons surviving longer. And said, wow, good, that's what we want. That's Anders localization. At some point, one of his former colleagues and others said, no, you might be wrong. There might be another effect. And the problem they basically had is that to get some light through the sample, they had to increase the intensity of the laser a lot. And then even white paint gets some fluorescence. And this was just the lifetime of the fluorescence of the white paint. And some years later, Georg Maret, he put a filter into this. And if you put the filter and just look at the less scattered light, this tail here disappears. So, okay, fluorescence. So these were the two main groups who worked on Anders localization of light. And they had very nice experiments which showed us the problems you can face, so that's very important, and all the models they use to understand what can happen. So despite the fact that these two papers could not prove that there's Anders localization of light, they are very important pioneers in the field, so I really owe a lot to these two groups to understand the whole physics of Anders localization of light in disordered system. But so it's still not observed. Okay, so this means that we are still in business. Maybe we'll see it, maybe not. We'll see. We have not seen it so far. I can spoil the end of the talk. We have not seen it neither, but we continue working on this. And during our way towards Anders localization, we discover other things which are interesting enough. So what we do is now we replace this semiconductor powders and white paint by cold atoms. So we have to do first our benchmarking experiments. So we have our cloud of cold atoms. We come with the probe beam in here. So there are different things. We can look how much photons go through the coherent transmission. And so if you're on resonance, then the atoms are very efficient scatterers and nothing goes through. That's the black points here. So that's the atomic resonance. So we have the atom levels. If you're on resonance, they scatter a lot. Nothing goes through. That's the black points here. And if you go out of resonance, light goes through again. That's the black points here. So if you plot this on the scale as a function of the optical thickness, then you see that these black points here follow an exponential law, and that's Beer-Lambert's law of transmission, a very well-known effect. And we just check that we can do this with our cold atoms. One advantage of cold atoms is that every photon which is scattered by the atoms, it comes back out as a photon. So we don't have any heating like transfer to microwave or infrared photons. So all the photons which don't make it through, they have to go somewhere else. And so I will divide the world into backward and forward direction. And so I will look here in the on the red points here. I put the detector here, and I look how much light goes through around the forward direction. And I see the red points in here. And if I plot this as a function of optical thickness, I find these points here. And the tail here decays like 1 over L. So that's the equivalent of Ohm's law, but now for photons. Okay, so these are results of a random walk model, and we just checked that we also can recover this. So that's my Eiffel Tower picture here. We can do this as well with our cold atoms. So that's just benchmarking that we control things, and it's important to know the numbers. So this is just to show that we know what we do. Then we can also do time-dependent experiments, like Maret did. So we learned from the people who also go for time dependence. In cold atoms, timing is very convenient because typically you go from picoseconds, which you would have in white paint, to nanoseconds or even microseconds if you go for cold atoms. So this means that the technology is much easier to handle. So here what we check, so we come with the laser beam, we switch it off, and then we look at how long does the photon stay in the system when we switch off the laser. And these are some experimental curves for different number of atoms in our system with different optical thickness. And we see if you have a large optical thickness, then the photons stay in the system for much longer than in a small optical thickness. And from this decay time here, you can extract the mean free path and the transport time and transport velocity, diffusion coefficient. And so one thing we measure from this is that we get the transport velocity, which is many orders of magnitude smaller than the speed of light in vacuum. So that's really a quite interesting result. This means that if you have these atoms, which are like a very narrow resonances, they act like small cavities. So photon goes on one atom, stays on one atom for a long time, and then goes for the other atoms. So the diffusion coefficient is very small, but it's not due to localization, under-localization effect. It's just due to this very narrow resonance we have in the cold atoms. So this is something we can measure. Just as a side note, we could even make this transit velocity smaller than the speed of light, than the speed of the atoms, which means that we can have the photons, the atoms moving faster than the light in this system, which is a little bit interesting, intriguing, but that's something we can do by exploiting this resonance of the atoms. Okay, then now we want to go beyond this random walk model, steady state Eiffel Tower picture, or this time-dependent effect. We want to see the interference effect. So we know that, so in a random walk, we have a diffusion coefficient, which is the square of the mean free path divided by the time constant to make these jumps. But we know that photons are waves, and so there will be interference effects. And so one prediction of this contribution to interference is that the diffusion coefficient will be reduced by this number KL. So that's the Uffe number here. So if KL is very large, so if the photon travels long distance before changing the direction, then this correction here is very small. So you recover the standard diffusion coefficient. But if KL is getting smaller and smaller, then at some point you might get a regime where this diffusion coefficient will be 0, and that's where you expect under-localization. So that's this Uffe criterion I mentioned before. And for this, you need to be able to scatter photon in the near field. So the mean free path has to be all of the wavelength, which is very hard to achieve. Okay, but so there have been some prediction how to see first corrections to this diffusion coefficient before you achieve under-localization. And this is shown here. So you come with a wave on a random medium. So there are different trajectories here. The incident field will do a random walk here and go back to detector. There's another path here, go to detector. And all these paths, you have to sum up the field on the detector here. And all these paths have random phases. So if you change a little bit the angle of detection, you get a speckled field, like shown here from a piece of Teflon. So that's just random interference effects. If you do a configuration average, so if you do manualization, you change a little bit the position of this sample here, you expect to get this fringe spectral pattern averaged out and get a flat intensity line. But there's something which is not included in this simple picture, which is correlated paths. So you have this path 1 here and the path 2 I just presented before. But you also have the possibility to do the reverse path here. So the photon will first hit the last scatter here, and in the sample do exactly the reverse path and go to detector. In that situation, this direct and reverse path have exactly the same path lengths in the sample. So it's like a Sagnac interferometer for opticians. And so you have to be careful before averaging out these two passes here. And so there's still a small path length difference here. So I can compute the difference of the path lengths of the direct and the reciprocal path here, which is shown here. So it still depends on the position of the first and last scatter, so which are random numbers. But there's a prefactor here, k in plus k out, which has wave vectors. So if k in plus k out is 0, so if I look exactly in the backward direction, then these two paths always interfere constructively. And so I have a pairwise interference effect. And if I do the averaging here, this gives me twice enhancement in the backward direction compared to all the other directions. So it's a little bit a surprising effect. In a random system, if I average, this multiple scattering effect gives me an enhancement in the average intensity coming back. So this is something we did with our cold atom experiments, and so using rubidium atoms, we saw this initially this first enhancement here around backward direction, but the rubidium atoms have some issues because they have an internal Zeeman structure. It's like small magnets which break time reversal symmetry, and so we had to build another experiment. We used at that time using strontium experiments where we could recover this interference effect. So this is a first effect which is called coherent backstretching or weak localization, which is the first pass towards Anders localization to show that interference effect can reduce the spreading. So basically the idea is I do a random walk and I go back a little bit more than on average. A random walk, it's not still freezing everything, but it's reducing the diffusion coefficient. So this is something we saw many years ago, and at that point the idea was just increase the density of atoms to get the mean free path of the order of the wavelengths to get localization, but we were not able to do this at that time. And then we did a big detour for maybe 15 years, or it's a big detour, to study something else. And this something else is to try to do some modeling. So we go back a little bit to ab initio modeling. So with cold atoms, we are able to do things starting from Hamiltonians. And so what we did is we came up with a model which we call the coupled dipole model. And the idea is the following. So every atom here is a dipole and is exposed to the driving field of the laser here. So the dipole beta here, the amplitude of the dipole beta j here, is driven by the phase and the amplitude of the driving laser here. And it has a free evolution, which you can get from just Hamiltonian optical block equations on single atom physics. But then there's another interesting term here, which corresponds to the field scattered by dipole M onto dipole J. And this is the collective effect, which is described by this green function here. And so you can solve these coupled equations. If you have n atoms, you have n coupled equations. You can solve this as a function of time or in steady state. And once you know all the dipoles, you can also compute the field, which is something we detect because we don't detect the atoms, we detect always photons coming out of our vacuum chamber. So we can compute the field here. Okay, and with this, we checked in steady state again first the results. So the blue curve here is the result of the coupled dipole model I just showed previously. So I come in with a plane wave on my cloud of cold atoms, and I first see a very bright spot in the forward direction, which is this very large peak here. And this corresponds to the kind of mean field effect. If you would replace this random cloud of cold atoms, but just by a homogeneous dielectric sphere of glass, this acts like a lens, and this is just a forward refraction of this lens. And so this is part of the coupled dipole model, and it has been shown in an experiment in JILA in the US quite recently, because basically to measure this, you have to almost look in the laser beam, which is a little bit difficult to do technically, but they were able to do this, so they could see this enhancement in the forward direction. Then the blue line, if you look at this random direction, there's a kind of a speckle field. If you average this, you get the blue line, which is hidden behind the black points. And the black points are a result of a simulation of random walk without interference effect. This shows that this previous model, this coupled dipole model, also includes multiple scattering and has this random walk included. And most interestingly, this coupled dipole model also has this coherent backscattering peak around the backward direction. So it has this mesoscopic interference effect included, which is the onset of localization effect. So we think that this model has everything we need to bring us towards Anders localization. So in time dependent, so always steady state time dependent. In time dependent, what you can use the same equation and you switch off the laser and you look at how this coupled dipole model shows you how the light decays. And so the dotted line here on the semi-log plot here would be the decay of a single atom. It has a lifetime, it's an exponential decay. If you have many atoms, what you see is that there is a faster decay, which we call super radiance, and the slower decay, which we call sub radiance. And so that's a prediction of this collective effect of atoms. So it's not included in the random walk model. You never get this faster decay. So this is really kind of a interference effect. And so what we studied many years ago numerically is how long is, what's the lifetime of these subradiant modes as a function of the optical thickness, and the decay rate goes like 1 over the optical thickness, so the lifetime goes like the optical thickness. So we have a predicted scaling how long photons stay in the system if you change the size of the system. And so this is something we did in the experiment. So the experiment was a little bit difficult because if you switch off the light very quickly, this subradiant modes, they stay in the system for a long time, which means that they're very weakly coupled to the outside world. But reversely, it's very difficult to inject energy into these modes because there's a very weak coupling from outside world to these modes. So this means that the amplitude of these separated modes is very small, and so you have to be able to switch off a laser quickly without any technical effects. So this was not an easy experiment, but okay, so, William Guérin was able to do this. And so what we see here is if you switch off the laser, there's a fast decay over 3 orders of magnitude, and then you have a slower decay here. And if you change the optical thickness of our cloud, we see that the lifetime of these modes increases. And also we showed that it does not depend on the detuning, the amplitude changes, but not the slope. And if you plot all these curves on a single curve here, we could show that the lifetime of these subradiant modes scales like the optical thickness as predicted by this Dicke model. And what's important here is that this is not just a few percent effect, it's a 2 orders of magnitude. So we could increase the lifetime of the photons by a factor of 100 by this subradiant model. So we can keep photons in the system for a very long time due to this Dicke subradiance model. So that was probably the most surprising result we had so far in our group from the last 20 years. But okay, so the current backtracking is something people have done in other systems, but this has never been done before. So this is something which is now being exploited for many different systems in quantum technology to use this super and subradiance models to do different devices. Better lasers, better clocks, better memories. And so this could be used at some point if you control the system differently to make a quantum memory based on this interference effect. Okay, so in particular, so William Guérin now changed the experiment from a random sample of cold atoms to get an ordered sample. So he put a lattice here, so you can trap the atoms in like pancakes. So you can order the positions of the atom a little bit, and he looks at this is the equivalent of a Bragg mirror, and now he is able to do an efficient Bragg mirror with atoms, and then you can control the direction of the emission of the light and where it goes. So he's looking at Bragg reflection. This works, and he has been more recently being able to do optical switching, and now he's going to see if you can do the equivalent of a gate with, so you put photons in the system, and then you can decide afterwards where the photons go, either in one channel or the other channel. So it's not just a memory with input-output, but a memory where you could switch between different directions afterwards. So it's a 3-port channel gate somehow. And so that's the next thing which is going to be happening on this experiment. Okay, so but coming back now to Anders localization, so we took our coupled dipole model and extract an equivalent effective Hamiltonian out of this, which is shown here. So now I forgot about the laser. It's like if you have an harmonic oscillator, you can always either look at how the pendulum swings. Okay, it's a driven dynamic system, or you look at the energy levels of this harmonic oscillator. So now I look at the energy levels of this harmonic oscillator. So I take an effective Hamiltonian because it's an open quantum system. I have an imaginary part everywhere, so there's a lot of eyes everywhere. So it's not a real Hamiltonian; it's an effective Hamiltonian. I have the single atom physics here, so that's a population of every atom here, and the decay and the free evolution of single atoms. And that's the collective part here. It's how the excitation jumps from one side to the other side with the coefficient here, which was already used in the Anderson paper here. And this coefficient here now has near-field terms. Near-field terms here, 1 over r cubed, that's near-field dipole-dipole coupling term, and far-field terms, that's the radiation properties of light scattered by dipoles. And so it's very similar to the Anderson model. I have randomness here. I can put randomness here, and I have hoping here. So it looks like the generalization of the Anderson model to an open quantum system. And I can look now at the eigenvalues of this effective Hamiltonian. These eigenvalues now are complex. There's a real part here, so that's the energy shift of this these eigenvalues, and there's a decay lifetime of this. And so, depending on the model I use, I can use a simplified model where I just take the far field radiation pattern, the 1 over r, which is what we call the scalar model, and I find very long lifetimes here. But if I do the real more complicated model where I take the near field dipole-dipole coupling term into account, I see that the lifetimes are not as long. And so this was something which was a little bit a surprise by the community, because typically in the 70s, people thought that microscopic details do not matter. There was like a universal scaling theory for localization, and it's more general, it does not depend on details. And here we see that the details of this dipole-dipole model you consider is affecting the lifetimes very, very strongly. And so you could use this to look at the Anderson localization prediction, and there are different criteria how to characterize this. There's a scaling function beta, which was produced by, so the experts call this the Gang of Four paper, where you could find the transition. So in 1 and 2 dimension, you always localize, and basically the idea is that in 1 and 2 dimension, if you do a random walk, you always come back to the point of origin. But in 3 dimension, it's not sure. You might not come back to the point of origin. And so that's why 3 dimension is the more challenging part. And in 3 dimension, there's a scaling function, so that's shown here. There's a scaling function here. So in 1 and 2 dimension, you always localize, but in 3 dimension, there's kind of a critical density here. So that's this KL equal 1, which where we recover the Joffe-Regel criterion, even if the Joffe-Regel didn't really consider this initially. And so what we can show numerically here is that if you take the simplified model without the near-field dipole-dipole coupling term, you indeed find a phase transition. But if you take the complete model, the phase transition is disappearing. So there's no Anderson localization of real photons in the coupled-dipole model. So this was first shown by Sergei Skipetrov and his collaborators in 2014. We come a little bit later. So if you see, if you come a few months later, this happens to your paper. So that's okay, that's how it is. But so the idea is that real photons which have polarization and near-field dipole-dipole coupling, there might be no Anderson localization. And so this is a good explanation why no one saw it, because it does not exist. So that's a sufficient explanation why all these experiments by Larendyk, Maret could not work, because it doesn't exist. Okay, so this is like a no-go theorem for Anderson localization of light in dipole scattering, electric dipole scattering models. Okay, so that's a very important paper for this effort. But as usually, if there's a no-go theorem, people are smart enough to find ways around. And very quickly, Sergei Skipetrov himself found a way how to overcome his no-go theorem by applying magnetic field to this system, which is a kind of a strange idea, because usually magnetic fields break time reversal symmetries. So how can you enhance localization by adding something which you should avoid? It works. So he showed that applying a strong magnetic field, you split the Zeeman degeneracy in the excited state, and 2 transitions see the localization and 1 doesn't. But so you can recover Anderson localization by applying a strong magnetic field. The problem is that you still need to fulfill the Joffe-Regel criterion, which correspond to very high densities of atoms, 10 to the 14th atom per cc. I don't know if yesterday you got the numbers we have so far in our experiments. We are like a factor of 100 or 1,000 below this. So it's very difficult to get this number here. So it's, but it in principle can exist. Okay, but you need to apply magnetic field, which the semiconductor people and the white paint people didn't apply. They cannot change this resonances here in these condensed matter samples. With atoms, we can do it. So in principle, that should be possible. But then I came to discuss with a colleague from nuclear physics about another toy model where we came back to the Anderson paper I mentioned initially. So that's the Anderson model here with Hamiltonian on-site energy and the hoping from one side to the other side. So that's the Anderson model. And we added the quantum open part to this channel. Yes, okay. So we opened these channels here, and what we found is that if you open the Anderson model, you find that again there's this super radiant decay and the sub-radiant decay. So we have to divide the world into fast decaying modes and slow decaying modes. And if you take the fast decaying modes, so this is the diagonal disorder, the energy disorder on the side, and this is how much you open. If you don't open, you have this line here, you have the Anderson transition at 16.7 omega, that's the Anderson transition. If you open the system a lot, then this transition disappears for the modes which are strongly coupled to the outside world, okay? But for the sub-radiant modes, even if you open up the system very long, the Anderson transition survives. So basically, this means that in this model, the sub-radiant modes, they somehow live in the closed system, so they don't care about the coupling to the outside world. That's why this Anderson model survives. Then we have now more recently we applied this to our coupled dipole model, and we because that previously was a toy model. So this is the coupled dipole model, and again, if without diagonal disorder, there's no localization, only extended state, and if you apply sufficient amount of diagonal disorder, we should be able to recover this localization. So there are two ways now, two proposals how to recover Anderson localization in cold atom systems: a strong magnetic field, high density, or diagonal disorder. And the one advantage here is that we don't need high densities. So this can work also at lower densities. So that's the situation. Two ways, no one has seen it, and we are now working on this. So we are preparing, time is short, so this is the technical part for us, very important, because that's where we spend our time. How to detect this, so we are going to inject energy in the middle, as people in matter wave experiments have been doing. So we found a nice way how to inject. So the problem is, if you have a big sample of white paint, how you can start with the photon in the middle and see how it spreads. We found a way with light shifter atomic physics how to inject a photon in the middle of the sample and then see how it spreads. And we could do the first benchmarking that we can indeed increase follow how this light spreads from the center. So that was a recent experiment we did. And this might be a good technical way how to check for localization, not only going through the sample, because if you go through the sample, you first have to touch the boundaries, and the boundaries are not well localized. The localized modes are in the middle. So if you come from outside, how to go to the middle directly? That's how we prove. That's what we proved here. We also showed that we can use an ancillary transition here to make the light sheaths of these atoms differently. So we can induce like a magnetic field, but now with lasers, which is more convenient because switching on and off magnetic fields at the time scale of milliseconds or below or microseconds is difficult. So we showed that we can do optically induced magnetism. That's something which we recently did. Technically things, but important for the experiment. So all this takes, every part here is always one PhD project. So everything takes a little bit of time in these situations. And then here is some simulations I did. So if you start from the excitation in the middle, so if you have a low density, the excitation very spreads to the whole system. If you have a high density, where you fulfill this Regel criterion, you would see that this spread will be frozen. That's what we like to do. And so that's good. So we also tried this with the diagonal disorder model, where unfortunately what we saw is that with the diagonal model, without diagonal disorder, it spreads as expected, but even with diagonal disorder, it spreads. And so this means that this technique to detect localization for diagonal disorder is not good. And basically what happens is that the partition ratio goes up and then goes down, the fractal dimension goes up and then goes down. So initially we spread and then we get a lot of localized peaks situation. So it's not as easy to detect as the other approach, two approaches, and the diagnostic will have to be adapted. And with this, so that's what we want to do. Go for higher densities, look at diagonal disorder, and always look at these localized modes. And I think I have one slide here. Just, so what is the conclusion of all this? So we have a lot of fun with our cold atom experiments. So cold atoms are very good to test collective atom-light interactions. I hope that's what I could convey to you. Cold atoms are already used in a lot of quantum technologies, of course, in sensors, gravimeters, memories. People do quantum simulations with cold atoms or quantum computation. Disorder is still a little bit put aside, but there will be disorder in all these type of systems. And so we study in particular how disorder can affect transport in this type of systems. And we also now do things with other kind of quantum open systems, but that's a different story. And with this, I thank you for your attention.
Maybe I start with the first question here. So you were showing like the walk around, and you looked at the scattering and the interference. For me, this was not kind of clear, because if I consider the optical theorem, I would say, well, I could kind of go around. And so if I see interference and constructive interference in one direction, everything else should go down. Can you comment on that? Because in principle, like we see a curve and then we see additional peaks in that one.
Yeah.
So where's the energy going?
Yeah, energy conservation. So people were discussing this for quite a long time, and people tried to do experiments. And there's been one paper published which is a little bit controversial, but okay. The zero order response to this, but no one really checked it quantitatively, is that if you look at let me just get back to this.
Exactly this one, like where we see the two curves.
Yeah.
And
so the extra peak here comes from a reduction in all the rest. But because this angle here is very narrow, the total energy in this peak here is very low, because it's only in the forward direction, and all the other directions will be reduced. So people don't know where this destructive interference, if it's isotropically reduced or if there's some specific angle where it's reduced. But it's difficult to compute. You need much better signal to noise, because the total energy in here, because the solid angle here is very small, 10⁻3. So you need to have an excellent signal to noise ratio to study the reduction. And no one has a quantity. So the conjecture is that it has to come from all the rest, of course. It has to come, there's no way. But is it spread evenly, or some people say there's a reduction in some tails here, but it's not fully satisfactory being shown, neither experimentally nor numerically.
So there are very interesting experiments also done very early in atomic beams by Ezekiel, like where they look at the scattering in all directions.
Yes.
And I think there are more recent experiments, by the way, by Ferdinand Schmidt-Kahler on a single ion, actually in a trap.
Yes.
Like I think this is closely related. And just a follow-up question, like in the backward direction, you see this factor of 2. Is this also given by the, if you will, the destructive interference of the incident wave, such that you have an absorption event at all?
So the going backscattering is usually discussed in the what the people call independent scattering approach. So they make loops. So they have a diagrammatic solution. So they add up all these scattering events, and then they add the reverse path. But there are other loops which would go from here to here and then here and go out, which cannot be solved analytically in this diagrammatic approach. And so people have just assumed that it's negligible. And here the relevant eigenmodes are independent atoms. That's called the independent scattering approach. And then you add diagrams to this. And in the Dicke model, the eigenvalues are extended eigenmodes. So it's coming from different sides. So either you assume the eigenmodes to be collective modes, and then you see how the light is coupled from one eigenmode to the other eigenmode, or you go from independent atoms. So there has been no connection between these two approaches. So this destructive, so if you go from Dicke kind of destructive interference to going backscattering, somehow you have to connect these collective modes to independent atom modes, and this has not been done.
Okay, thank you very much. There was another question up here. I just deliver the microphone.
Thank you. So actually, I have a technical question and an application question. The technical one I didn't get. How did you manage to insert the photon into the Cote Atom Cloud? That was too fast, or maybe I didn't follow. I don't know. And the other one is, I mean, imagine you can do that. You could do this, yeah. So you could trap a photon in that cold ion cloud. What are possible applications? I mean, is there a communication application with this? You carry around photons? I don't know. Yeah. So I would be curious. Yeah.
So that's what at the end I went quickly on this. So actually, we were inspired by experiments done in the group of Alain Aspect and Vincent Josse in Palaiseau, where they used matter wave to study localization. And so what they did is they prepare a Bose-Einstein condensate somewhere, so it's a wave, so a matter wave, and then they switch on the disorder. So they switch on the sample as a function of time, because they use optical speckle pattern, which they can switch off very quickly. So they have the atom here without disorder, and then they switch on the potential with the laser. So the question is, how can we switch on and off the sample after preparation? So what we did is the following. So we have our cloud of cold atoms, which some of you might have seen yesterday. And so we look at the scattering on the transition from the ground state to the first excited state here in the green. That's our scattering process. So we want to have a lot of atoms here which scatter the photon. That's the sample. So what we can do is we can add another laser beam between this excited state and then the higher lying state here in the infrared. And this induces a light shift on this excited state here, which makes this energy level being shifted. Now, if we, so this is the freeze 3p1 transition here without light shift. And if we light shift the laser, so we take this additional laser, we focus it in the middle of the cloud. So only these atoms here will be light shifted and those atoms here will not be light shifted. Now we come with a laser which is out of resonance for the free atoms, but will be only resonant with the shifted atoms here. So the laser will excite nothing here, but here, suddenly they're on resonance, and then we excite the atoms in the middle. And then we switch off this light shift laser, and then suddenly the photons are in the middle, and they see all the other atoms. And that's why. And so what we can do is we can control. We check that this is then giving a diffusion process. We can also switch off things and keep the light shifter on, and then we can change the frequency of the photons which will propagate. So we can control where we launch the photons and at what frequency we launch the photons. We should be able, but we did not do yet, we could also maybe control the phase of the photons we launch, like in what direction do they go. This we have not shown yet, but that should be possible in principle. So we have some control on the initial condition to see spreading afterwards. And so this is something which is, to some extent, it could be generalized for atomic systems or resonance systems where you can control the resonances with other lasers to get rid of boundary effects. Because sometimes boundary effects are an issue. So if you want to go deep inside the sample, so that's the way how to go inside the sample if you can control the resonances of your system. So with wide pane, I don't know how to do it, but with atomic or NV centers or whatever, you might be able to do this. I don't know if that's the explanation, but...
Do you see possible applications?
Well, so one thing is that if you can, that's why we do this. We think that the long-lived modes are longer lived in the middle of the sample than on the boundary of the sample. So if you want to increase lifetime of systems, if you can put it in the middle of the center, you're protected from defects on the boundaries. So maybe you can do better lifetimes. I don't want to see better memories, but okay, you can maybe reduce the effect of disorder on the boundaries of the sample. Or you could tune where to prepare this. If you have a sample which has some defects, you could choose where to put the excitation by changing the position of this light shifter. You could control positionally where you excite the sample.
Okay, here's another question.
Yes, so you spoke about switching on disorder. Does that mean you introduce some randomness into the system?
Yeah, so yeah, exactly. So we have two different types of randomness we can exploit here. One is the randomness of the position of the atoms. If we don't take a lattice, or we can either decide to put the atoms on a regular lattice or just leave them free in a random position. So far, we mainly have used random positions. So that's one randomness. We could change it. And that's what I showed with this Bragg reflector. So we can also put it into lattice in 1D, 2D, 3D. So far, we focus, we in Nice, also in France, are very strong on disorder. And there's a big expertise, not only in our group, in Paris, in Lille, in Grenoble. So France is quite good in disorder in this system. And so we still focus on the disorders. We don't really push too much to put it on lattices. Other people are very good in this, but we don't. And the other type of disorder we can do is take this laser here and use a speckle field on this laser. So then every atom here will see a different shift. And this will correspond to the randomness on the energies of every atom. So there's a position where the atoms are, and we can put a randomness on the light shift. So we can also make a randomness, controlled randomness with the light shifter we can impose with the SLM or with the speckle field. So a different type of disorder, that's why point of diagonal disorder, we would use this laser here to induce a controlled diagonal disorder on the energy levels.
Somehow, at least to me, seems as if you could also have very controlled disorder.
Yes.
So you could really control that there is no periodicity in your lattice.
Yeah, so that's in principle possible. We don't want to put too much. We want to have a generic randomness. That's what we want to study. But so for the light shifter with SLM, we can put the light shifter on the lattice. So that's the easiest thing. Putting the atoms on lattice, it's easy to put it on the lattice, but not to have a uniform filling. Uniform filling is a little bit more complicated to do. People have done it, but it's a little bit harder to achieve. So we don't want to go into this direction for now.
Okay. Thank you.
So the session I would like to close. Very nice. I think I'm pushing hard to be on time. Let's thank Robin again.